Hello and welcome to our talk for APPROX 2022. My name is Martin Knark and I am presenting our paper, Maximizing a Submodular Function with Bounded Curvature under an Unknown Knapsack Constraint. This is joint work with Max Klim, and I will directly start and I will tell you what is the problem we are facing. So we are looking at the knapsack problem. We have a finite set of items and we have a set function f, and the set function has several properties. We are looking at a set function that is submodular, monotone and normalized, and we are looking at a small example here how we can visualize such functions. We have 4 items. We have a green item, blue item, red item and a violet item, and the value of an item is given by the numbers it contains. For example, the red item contains the 4 and the 8 and these other 2 4s, so the total value of the red item is 20. For the green item, the total value would be 12, and the value of the red and green item together would be 28, because this 4 is contained in the red and in the green. And the standard knapsack problem then is maximizing this set function f over a subset of items that fulfills the knapsack inequality, which says that the sum of the items is not allowed to exceed the knapsack capacity. So we have the set of items, and what is the special part about our problem is that the knapsack capacity C is unknown to us. We don't know the capacity and have to build a solution that works for all capacities. And one special property we are also looking at, this is the curvature for the set function f. The curvature is defined by 1 minus the minimum over all items, where we are looking at the value the item can give to all other items divided by the value of the item. As a small example, in here, this minimum would be given by the red item. The value this item gives to all other items would be 4, only this 4 here in the middle, which is not contained in any other item. And the total value is 20 of the item, so we would have 4 divided by 20 is 0.2, and 1 minus 0.2 is 0.8, so the curvature for this example would be 0.8. So let's take a look how a solution to the knapsack problem with unknown capacity can look like. And these are so-called policies, and they govern the order in which items are added to the knapsack. There are 3 different kinds. The first one are universal policies, and here the order in which the items are added are the same for all capacities. This can look like this. We are starting with an item I1, and either this item is packed if it fits into the knapsack, or it is rejected if the size of the item is too large for the knapsack. But no matter if it's packed or not, we are continuing with the same item I2, and again looking if this can fit into the knapsack or not. And if an item is packed into the knapsack, it will stay in the solution forever. We cannot remove it again from the knapsack. Other policies are adaptive policies. Here we can have different orders for different capacities. This can look like this. We start with an item I1, and if the item is packed, then we are continuing with an item I2. And if the item I1 is rejected, we would continue with another item I3. So don't have to continue with the same item. And this looks like a binary decision tree we have for adaptive policies. And last but not least, there are also randomized policies. Here, an item is chosen by the policy with a given probability, but we are not looking into randomized policies that much in this talk. When we evaluate such a policy, we are looking at the output of the policy for a given capacity. This is pi of c. And then we are looking at the robustness, and this is the worst case over all capacities of the value of the output of the policy pi for a capacity c divided by the optimum output of the capacity c. And before we come to our results, we're looking on some related results. Here we are first stating one result by Wolsey about so-called modified greedy algorithm for the case with known capacity. This is a 1 minus e to the power of minus x approximation, where x is the unique root of this equation. And then we have two other results for the case with the unknown capacity. The first one is the result by Disser et al. They give a type 1/2 robust universal policy for linear functions f. And the second one is by Curvature et al. They are giving, they have two results. The first one is a 0.06 robust adaptive policy for submodular functions f, and the second one is a 0.316 robust randomized policy for submodular functions f. And we can look at the landscape here. We have on the x-axis the curvature c, and on the y-axis we have the robustness alpha. And the first result of Disser et al. Is for linear functions, so this is when the curvature c equals 0, and they give a policy that equals 1/2, so their result lies there. And because this result is tight, we also know that it's impossible to reach this gray area here with any policies for all curvatures between 0 and 1. And then the two results of Curvature. The upper one is the randomized policy for submodular functions f. Submodular functions do we have when the curvature is 1, and they can generalize to all other curvatures. That's why we added this horizontal lines here, the dash one for the randomized policy and that normal line for the adaptive policy. So how are our results compared to these? First of all, we give an analysis for the modified greedy algorithm. We are looking to the, I will show you the greedy algorithm on the next slide, for submodular functions and generalized to the curvature c. And what we obtain is here 1 over c times 1 minus e to the power of minus c times x approximation, where x is the unique root of this equation for values between 0 and 1. And then we have a result for the knapsack problem with unknown capacity. So this is for the known capacity, the greedy algorithms. And for the unknown capacity, we can show that there is an adaptive policy that has the same robustness factor as the modified greedy algorithm. And in this landscape, this looks then like this. Here we added this curve. This is given by our adaptive policy, and it nicely connects the result from Disser et al. In 1/2 for linear functions, and is smoothed over the curvature, and still improves the results from Curvature et al. For the randomized policy here and for the adaptive policy down here. Okay. So before we come to this adaptive policy, we will take a look at the greedy algorithm. And here we are looking at the greedy algorithm for linear functions f. And we have a small example down here. We have different items here in red, and their size is given by the length, by the horizontal length. And down here we have the knapsack with the capacity, and we want to add items now to the knapsack. And the modified greedy algorithm, we go to the steps. First, discards all items that are larger than the capacity. For example, this really large red item here, this would exceed the capacity as a single item, so this is discarded. Then the algorithm continues to build a greedy solution, and therefore it adds items that are maximizing the density that is given by the function, by the value of the item divided by the size of the item. The density is shown at the items by their opacity. So the item on the left side is the most densiest, and then they reduce to the right side, and the item down here, this is the less dense item. So the greedy algorithm is starting with the left item, and then continues to add more items based on the density, I2, I3. And you see that we name the items by the order, and they are added to the knapsack, so that we have all items listed from I1 to I5. And this is what we call the greedy order. Of course, the knapsack cannot add all these items. The capacity was already here. And what the greedy algorithm does is that it stops if an item is larger than the capacity when we want to add it, and this would be the case for I3 here. And then we have two solutions. The first solution contains the items I1 and I2, the set of items that fit into the knapsack. And the second solution is this item I3, where only a fractional part of the item would fit into the knapsack. And what the algorithm does is now that it returns the more value of these two solutions, either gk where k is given by the number of items that fit into the knapsack, G2 in this case of this example, or the fractional item ik plus 1, I3 in the case of this example. It is well known that this algorithm is a one-half approximation, and what this et al. Could show is that their universal policy is as good as a modified greedy algorithm for all capacities, and thus they receive with their universal policy a one-half robust policy. And the question to us was now, can we do such things also for submodular functions there? And therefore we are looking for to the modified greedy algorithm generalized to submodular functions. And the only thing that changed here is the formula for which decides which items to pack next. Here we are looking now not at the density, but we are looking at for an item how much value does it give to the solution at hand. So we have a solution at the moment j minus 1, and we are looking how much is item I adding to this solution, and then we are dividing this by the size. And the item that is maximizing this term, that is added to the solution. This is a natural generalization. If we have linear functions here, then this simply simplifies to the density we had on the last slide. But note that this changes here a lot. If we start with two different items, so consider two different capacities, where we start with two different items at these capacities, the greedy orders, they are created by this step 2a here, can look completely different. And this is different to the linear case, and this is why we totally cannot expect universal policies as good as this modified greedy algorithm. But there is another negative result here, that is that we also cannot find adaptive policies that are better as a modified greedy algorithm for all capacities on all instances. And I will show you why in a small example, and this is the example from the first slide again. The values were given by the numbers inside of the items, and the sizes are also added here. The red item has size 10, the green item size 12, and the blue and violet item size 5. First, let's look at the greedy order for the modified greedy algorithm. And the modified greedy algorithm starts with the most densiest item, and this is the blue item with the density of 12 divided by 5. And then the second densest item would be the red item, but the value of the red item is now reduced because we already added the blue item. And then the red item only has a density of 12 divided by 10 left. And now the violet item with 7 divided by 5 has a higher density, and this is the second item in the greedy order. Then the value of the red item is reduced again because we added the violet item. And then the green item is more dense than the red item, so the green item comes in the third place, and the red item is the last item in the greedy order. If we now look at different capacities and what is the output for this capacity, we'll see that the greedy algorithm returns the red item for capacity 10. Why is this? The green item is too large for this capacity, and that's why it is discarded directly at the beginning of the algorithm. Then the blue and the violet item are added to the greedy solution, and they sum up to a value of 19. And then the red item is the first item that exceeded the next knapsack capacity, and thus as a fractional item is checked if it has more value than the greedy solution, and in this case it has a value of 20, and the greedy solution is the blue and violet item together, they have a value of 19. That's why the red item is output or returned by the greedy algorithm. The other cases are a capacity of 12. Here we have the blue and the violet item as an output, because now the green item is considered as a fractional item, and the green item has less value than the blue and the violet item. And for the capacity of 22, the output is the blue, violet, and green item, because they as a greedy solution have more value than the red item. But now look, we take a look on different start items. So we consider every item as a start item, and we will see that there always is a capacity where we are worse than the greedy algorithm. So if we start with the blue or the violet item, we have for the capacity 10 that our solution can only be the blue and the violet item, but this is worse than the output of the greedy algorithm, which was the red item, or the capacity equal to 10. If our policy starts with the green item, we have a problem for the capacity equal to 12. Here, the solution of our policy would be the green item, has a value of 12, but the greedy algorithm outputs the blue and the violet item, they have together a value of 19. And last but not least, if we start with the red item, then we are worse for the, we have bad solutions for the capacity of 22. We can either add the blue and the violet item to the red item, or the policy can add the green item to the red item. There are no other possibilities here in this small example. But worse, both are worse than the output of the greedy solution. You can simply calculate the values and you can see that. And that's why there are no adaptive policies for this greedy algorithm. But with a small change at the greedy algorithm, we can overcome this issue and find adaptive policies. So what do we change here? We have now what we call the alternative greedy algorithm, or short A-greedy. And what we changed here is only the condition for which we return the greedy solution or the fractional item. And the condition is now that we return the greedy solution if the value of the greedy solution is larger or equal to the value the fractional item adds to the greedy solution. And otherwise, if the value of the greedy solution is less than the item adds to the greedy solution, then we output the fractional item. Result at hand is that the value of the alternative greedy is less or equal than the value of the modified greedy, simply because the modified greedy always returns the better of the two solutions, and alternative greedy may return the worst of the two solutions if this condition is like that. Then there is, when we think, okay, this algorithm might be bad, but actually if we look at our worst case approximation, we saw that we received the same approximation ratios for both algorithms, and these are the approximation ratios you already saw on the results slide. That actually holds for the alternative greedy, and because of this equation also for inequality also for the modified greedy algorithm. And we will see in the last part of this talk that this alternative greedy algorithm can be used to derive adaptive policies. And for that, we are defining indispensable items. An item is called indispensable here if there exists a capacity C for which the alternative greedy algorithm returns this item as a fractional item instead of the greedy solution. And we will go through some properties of these items. They will be important, and therefore we have here also a small example to visualize. We have three items. They are building our greedy solution, I1, I2, and I3, and we have the fourth item, and this is an indispensable item. And also here is the capacity we are looking at the moment. So for this capacity, the item I4 is the fractional item and is output by the alternative greedy instead of the greedy solution. The first property we have is that the size of this indispensable item is larger than the size of all items in the greedy solution. This is a necessary condition here. And yes, from this condition follows the second condition, and this is that our indispensable item is also indispensable for the capacity equal to its own size. So we can easily see this here. If we reduce the capacity to the size of the item I4, like this, then we know that nothing can have changed in the greedy order until to this fourth item here, because all items by property A are smaller than this capacity. And so they are all considered still by the greedy solution, and also this item is considered. And of course, the condition for which solution is returned doesn't change, so this is still an indispensable item. And then we have the last property. This is a little bit longer. The first item that is larger than our indispensable item and that is changing this greedy order in front of the indispensable item. So it either goes to the first, second, third, or fourth position in this example. This item is either the first item in the new greedy order or it is an indispensable item. And why is this? Let's look at a higher capacity for which such an item appears. This will be the capacity of item, the size of item j. And now what the property C says, either item j is the first item in the greedy order, so then this is the case if it has the highest density of all items, or if it's changing the greedy order in front of the all indispensable item at any other place, then it is again an indispensable item. So let's add this item here. For example, after the second item I2, this looks like this. And we can easily see, yeah, because there are some items in front of this item has to exceed the capacity because its size equals the capacity, so it is definitely the fraction item in the greedy algorithm. And since it has more value, note that it is larger than the old indispensable item, and now it was chosen instead, or also instead of other items, but especially instead of the other old indispensable item, and that's why it has to have more value, and it has to have to add more value to the greedy solution than the old indispensable item, and then it definitely adds more value to the greedy solution than the greedy solution at the moment has. Okay, so these are the three properties, and now we are looking how an adaptive policy can look like. The first step, we are determine all possible start items. And these are the indispensable items and all items at the beginning of the greedy order. And we can simply do this just by looking at the capacity of every item, of the size of every item, and calculating for this capacity if this item is an indispensable item or if this item is the first item in the greedy order. So we have no problem to determine all these properties for all items. Second step is that we are sort these items in decreasing order, and we are adding the first one to our knapsack solution that fits. So we are starting with the largest one. If this fits, then we are continuing with step 3. And if it doesn't fit, we are looking at the second largest. If this fits, then we are continuing with step 3. Otherwise, we're looking for the next largest. So we're adding one item here in step 2. Only when all items are too large, then none of the items is added. In step 3, we are checking if this item in step 2 was an indispensable item. If this was the case, then we are adding this indispensable. We are looking at the greedy order and adding all items to our solution that are in the greedy order in front of the indispensable item. This is an important step. And the last step then is the fourth step. There we are only adding more items in the greedy order, so just adding greedy more items. Let's give an intuition why this gives an adaptive policy that is always as good as the alternative greedy algorithm. And let's first look at the case that the alternative greedy algorithm returns the fractional item, and this is an indispensable item then. Then we know this item is added in step 2 to our solution because it's contained here, and there can be no other item that fits into the knapsack or these capacities. So this item is definitely added here in step 2. So this step is clear. And then we also have the case that the alternative greedy algorithm returns the greedy solution. And then we again have two cases. We can add an indispensable item here in step 2. But then, so we know we want to come back to a greedy solution. We need to add all the items that come in the greedy order before the indispensable item, and this is what we are doing in step 3a. And with step 3a, we are back at our greedy solution GK. And if the greedy solution output by a greedy is even larger, then we continue to add these items in step 4. So we are also managing that step or that case. And otherwise, if also our first item was not an indispensable item in step 1, then it was the first item in the greedy order. And this is, of course, exactly what we want if the algorithm returns the greedy solution. And since we are also adding more items greedily in step 4, we are also managing to achieve this greedy solution. Okay, with that I'm coming to the end of this short presentation. Just make sure that both cases here are satisfied. And let's take a last look at a small summary. We looked at the knapsack problem, especially for submodular functions with unknown capacity. We have seen that the modified greedy algorithm does not can be used to achieve adaptive policies. That's why we looked at an alternative version, the alternative greedy algorithm. For that, we showed this approximation ratio for different curvatures. And in the last step, we discussed this adaptive policy here, which is as good as an alternative greedy algorithm for our capacities. And this gives us the result we presented at the beginning of this talk. which is this curve. Okay, thank you for your attention, and